In this video, we're going to learn about multiplicities of zeros. Just like our previous video, we'll work through some examples coming up with formulas of polynomials, and we'll learn how the multiplicity of the zeros affect the behavior of our function at the x-intercepts. In our previous videos, we learned about the factor theorem, which tells us that for polynomial functions, if a certain number is a zero of our function, then we have a factor of x minus that number in the formula for our function. But what if our formula has more than one of those factors? This is where multiplicities come in. For a polynomial function f, we say that a number r is a zero of f with multiplicity m if f of x has a factor of x minus r to the power of m. So the multiplicity of a zero tells me how many factors of x minus a certain number is in our polynomial function. Let's work through some examples to get a better idea of what we mean. In this example, we want to find the formula for a degree 6 polynomial that goes through the point 1, 2 with the following zeros and multiplicities. We see that negative 3 is a zero of our function with multiplicity 2, 0 is a zero of our function with multiplicity 3, and then 2 is a zero of our function with multiplicity 1. Let's first talk about what factors our polynomial will have. First of all, since negative 3 is a zero of our function, we know from the factor theorem that it has a factor of x minus negative 3. But since we're told that the multiplicity is 2, we not only have one copy of this factor, but we have two copies of this factor. So our polynomial will have a factor of x minus negative 3 squared. Next, since 0 is a zero of our function, we know from the factor theorem that our polynomial will have a factor of x minus 0. But since the multiplicity is 3, we know that we have 3 of these factors, so our polynomial will have x minus 0 cubed. And lastly, 2 is a zero of our function. From the factor theorem, we know that our polynomial will have a factor of x minus 2. But since the multiplicity is 1, there's only one copy of this factor in our polynomial. So we can write a 1 as the exponent here, but that's not necessary. Putting all of this together, we know that our polynomial function will look like f of x equals x minus negative 3 squared, which we can write as x plus 3 squared, x minus 0 cubed. We don't really need the minus 0, so just write x cubed. And then lastly, a factor of x minus 2. So now, what's the degree of the polynomial that we have here? The x plus 3 squared portion, if we multiply that out, will end up with an x squared. Then multiplying that with an x cubed brings us to x to the 5th power, and then multiplying by the x here brings it to x to the 6th power. So if we were to multiply everything out here, we'll have a degree 6 polynomial as we wanted. Just like before, we can apply a vertical scale to this function and still keep it a degree 6 polynomial with our desired x-intercepts. So out in front, we're going to multiply by a vertical scale a. Let's take a look at the graph of such a function. So let's type in the equation for the graph of our function. We have y equals, and for our vertical scale, let's choose 1/2 for now. So 1/2 times x plus 3 squared, and then times x cubed, and then times x minus 2. So we see here we have a polynomial function that's degree 6, and it has all of our desired x-intercepts. X-intercept at negative 3, 0, and 2. Remember that no matter how we change our vertical scale, we'll still have a degree 6 polynomial that has our desired x-intercepts. So if we change it instead of 1/2 to say 1/6, it's still a polynomial that has x-intercepts negative 3, 0, 2. We can introduce a negative in front of the 1/6 to make a vertical reflection, and you see we still have a polynomial that has x-intercepts at negative 3, 0, and 2. Next, what we want to do is we want to find the specific polynomial that goes through the point 1, 2. So on our graph, let's add on that point, 1, 2. We see that with our current vertical scale of -1/6, our graph gets really close to the point 1, -2, but doesn't quite pass through it. Let's set up the equation that will allow us to solve for the exact vertical scale. Remember that our function going through the point 1, 2 means that when we input 1 into the function, we get the output 2. So what we need from our function is that f of 1 equals 2. This gives us an equation that we can use to solve for our vertical scale a. So let's first write down what f of 1 is. We want to plug in 1 everywhere we have x in our function. So plugging in 1, we have a times 1 plus 3 squared times 1 cubed times 1 minus 2. So what we have here is f of 1. And what we want is that this expression equals 2. So let's set this equal to 2, which gives me an equation that we can use to solve for a. Let's simplify that left-hand side. We have a times 1 plus 3 squared would be 4 squared or 16, and then times 1 cubed, that's just 1, and then 1 minus 2 is -1. And on the right-hand side, this is still equal to 2. Simplifying that left-hand side further, we have a times 16 times 1 times -1. This gives me -16a equals 2. And so to solve for a, we just have to divide both sides by -16. So 2 divided by -16 gives me -1/8. So what this means is that when my vertical scale is -1/8, our graph will go through the point 1, 2. Let's check this. If we go to our graph and change the vertical scale from -1/6 to 1/8, we see that our graph now passes through the point 1, 2. So the degree 6 polynomial function that goes through the point 1, 2 and has the appropriate zeros and multiplicities is f of x equals -1/8 times x plus 3 squared times x cubed times x minus 2. Now, one last thing I want to talk about is how the multiplicity affects the behavior at the x-intercepts. Now, at each of our x-intercepts, one of two things can happen. Our graph can either cross the x-axis, or it can go up to the x-axis, touch it, and then bounce off. Let's look at what's happening at each x-intercept. At the x-intercept at -3, if we trace our graph starting from the left, we would go up towards the x-intercept, touch the x-axis, and then bounce off. So let's make a note of that. At the x-intercept -3, the graph goes up to the x-axis, touches it, and bounces off. Now let's go to our next x-intercept. At x equals 0, if we trace our graph before and after, so start on the left-hand side, trace our graph, we see that the graph goes towards the x-axis, touches it, and then it crosses the x-axis. And we also see a similar behavior at the x-intercept at x equals 2. If we trace our graph from left to right, we start above the x-axis. As we get closer and closer to 2, our graph touches the x-axis and then crosses the x-axis. So at the two x-intercepts 0 and 2, we would say that the behavior is the graph crosses the x-axis at those x-intercepts. So from this example, it seems like when the multiplicity is even, the graph touches the x-axis and then bounces off, whereas when the multiplicity is odd, the graph crosses the x-axis. Let's work through another example to see if this pattern holds true. In this example, we want to find the formula of the degree 7 polynomial function that goes through the point 0, 6, and it has the following zeros and multiplicities. -2 is a zero of our function with multiplicity 1. 1 is a zero of our function with multiplicity 4. And 3 is a zero of our function with multiplicity 2. Let's start by writing down the formula for a function with those zeros and multiplicities. We would have something like f of x equals Now, since negative 2 is a zero of our function, we know that it has a factor of x minus negative 2. Now, since the multiplicity is 1, we know that there's just one of these factors, so there's no need to write down any exponent here. Next, we have 1 as a zero of our function, so we know that our function has a factor of x minus 1. And since the multiplicity is 4, we know that there are 4 of these factors, so we have x minus 1 to the 4th power. And then lastly, 3 is a zero of our function, so we know that it has a factor of x minus 3. And since the multiplicity is 2, the function has 2 of these factors, so we have x minus 3 squared. And as always, when we apply a vertical scale to this function, it's not going to change the locations of our x-intercepts. So we can multiply by a vertical scale a out in front. Now, when we look at our factors here, we essentially have 7 factors of x minus a certain number. So here's one factor. Here, there are 4 factors of x minus 1. And then here we have 2 factors of x minus 3. So again, altogether we have 7 factors of x minus something. So if we were to multiply this polynomial out, we would end up with a degree 7 polynomial. Now, these double negatives here we can simplify, and we can rewrite our function as f of x equals a times x plus 2 times x minus 1 to the 4th power times x minus 3 squared. Now we want to find the specific polynomial that goes through the point 0, 6, which means that when I input 0 into my function here, we get 6 as the output. So what we need is f of 0 equals 6. This will allow me to set up an equation to solve for our vertical scale a. Let's start by writing out this left-hand side, f of 0. F of 0 means I'm taking my function and replacing the x's in our function with zeros. So on the left-hand side, we have a times 0 plus 2 times 0 minus 1 to the 4th power times 0 minus 3 squared. So what we have here is f of 0, but we want this to equal 6. So we're going to set this expression equal to 6. This again gives me an equation that we can use to solve for a. Simplifying the left-hand side, we have a times 0 plus 2 gives us 2. Negative 1 to the 4th power gives us positive 1. And then lastly, negative 3 squared gives us 9. And on the right-hand side, this is still equal to 6. On the left-hand side, a times 2 times 1 times 9 gives me 18a equals 6. And then to solve for a, we can divide both sides by 18. A would be 6 divided by 18, or 1/3. So what this means is that when our vertical scale a here is 1/3, our polynomial function would be a degree 7 polynomial that goes through the point 0, 6, and it will have these zeros and multiplicities. So our function is f of x equals 1/3 times x plus 2 times x minus 1 to the 4th power times x minus 3 squared. Let's take a look at the graph to confirm our findings. So to graph our function, we would graph y equals our vertical scale 1/3 times x plus 2 times x minus 1 to the 4th power, and then times x minus 3 squared. Okay, so that is our polynomial function, and let's confirm that it goes through our desired points 0, 6. So we see here we have a degree 7 polynomial that has the x-intercepts -2, 1, and 3, and it goes through the point 0, 6. Now, one last thing I want to look at is the behavior of our function at our x-intercepts. At each x-intercept, does the graph cross the x-axis, or does it touch the x-axis and then bounce off? Let's start with our leftmost x-intercept at -2. If we were to trace this graph, we see that our graph crosses the x-axis. So at the x-intercept -2, our graph crosses the x-axis. On the other hand, at my other two x-intercepts, at x equals 1 and at x equals 3, when we trace our graph from left to right, we see that our graph goes down to the x-axis, touches the x-axis, and then goes back up. Around 3, our graph goes down to the x-axis, touches the x-axis, and then bounces off. So the behavior of our function at the x-intercepts 1 and at x equals 3, our graph goes to the x-axis, touches it, and then bounces off. So just like our previous example, when the multiplicity is even, like 4 and 2, the graph will touch the x-axis and then bounce off at these x-intercepts. And when the multiplicity is odd, the graph will cross the x-axis at our x-intercept. And this pattern is true in general. If the multiplicity is odd, the graph crosses the x-axis, and when the multiplicity is even, the graph touches the x-axis and bounces off. It does not cross the x-axis. So in this video, we learned about the multiplicities of the zeros of a function. We learned how to write the formula for a function when we're given the zeros and multiplicities, and we also saw how the multiplicities affected the behavior of the graph at the x-intercepts.